All right, first of all, I want to thank you all for inviting me to California and letting me drop the mic. You're not supposed to drop the mic till the end, though, right? All right. Well, that's what happens. All right. Okay, so just by way of introduction, I spent 25 years doing big data cosmology projects. Things like the Sloan Digital Sky Survey and the Dark Energy Survey. I worked on big multidisciplinary teams to solve the kinds of problems that can't be solved by small teams. You have to bring together a lot of people to solve these challenges, right? So in a way, when I find a big problem like this that I think needs to bring together a group of people, that seems like a natural solution for me, so we'll come to that. In recent years, I have turned to education research over the last 10 years or so, and it really all grew out of the fact that there is a flood of data available now about learners and the context that they're in and the products that they produce and all of this that wasn't present 15 years ago. And I think it gives us a really fantastic opportunity to explore and improve higher education in a lot of ways. But the main way that I'm working on, the main challenge that I'm working on right now, is large foundational courses. And I want to work on these both in practice to design courses that are designed for equity, that create an environment that is inclusive, but that also are really effective. And I also focus on these courses in research. I think these courses provide fantastic laboratories for understanding what happens with learning as well, and that if we're going to teach a large number of students all at once, we should be very attentive to what happens. In other words, we should use them as a laboratory, as an opportunity for learning. So I want to talk about some of those things that are happening. I like to think on my chalkboard, so I'm going to use a bunch of little chalkboard cutouts in order to describe the work that I'm going to do. Let's start by talking about STEM foundational courses, and there's too much on the chalkboard to really look at, so I'll break it down into a couple of different pieces. Big foundational courses are important for students. I think everyone knows this. They are considered gateways to STEM disciplines by pretty much everyone who's involved. They provide students with very powerful signals about whether they belong in this discipline. This is the main place where people make up their mind about that. They also tell students something about the nature of fields. So when we talk about student values and how they might be reflected or not in the content of an introductory course, that's one of the ways in which they're deciding whether this is a field where they belong. All foundational courses, but certainly STEM foundational courses, face a special challenge in terms of the diversity of background, interests, and goals of their students. If you teach a junior level quantum mechanics class in physics, they've been through several years of regularization. So by the time they get to you, it's quite an easy challenge to teach them compared to what it is to teach introductory students. And that's one of the things that separates these large foundational courses from others. So they're very important for students. That's one feature of these. They're also super important for institutions, especially big public institutions. At Michigan, we have 110 large classes, that is to say 110 classes that enroll 200 or more students in them. Although they are only 1.5% or so of all the classes that we offer, they're responsible for 1/3 of all student credit hours. So a big part of the student experience happens in these classes, 1/3 of the entire student experience. Students pay $150 million a term in tuition for that 110 classes. And we spend $14 million a term teaching them. Now, this is not as bad a thing as it sounds, because the other 2/3 of the classes are money losers, and they're a very important part of the curriculum as well. There have to be cost centers that generate some of this. But I use these numbers with our institution to make the argument that if we need to make a somewhat bigger investment in these courses, it's not crazy to do so. Right? And I think everyone should think about knowing these numbers for their own institution. So they're important for institutions. And I would say, in general, these current courses fall short of everyone's ambitions. Right? Both students and faculty members struggle to achieve their own goals in these classes. Many of our students are not learning as much as they want to learn. Many of our students are not learning as much as we want to learn. It's too hard to teach these classes. There are many things wrong with these classes, right? It's also true that there are equity issues in these courses, which are widespread. Many of them have been long known, recognized, and nothing has been done about them. They're generally unaddressed, the equity issues that are present in these classes. And it's also true that even when research is done into equity in these classes, it's usually done by people who aren't part of the class. You know, we, the people who are teaching these classes, should be examining equity in these classes. And if there are problems with it, we should be working to fix it. Okay, so I got started in doing this work by thinking about equity in my own courses, big introductory physics courses, and I want to walk you through a couple of the steps in that process that are kind of sketched out on the board here. So the first was an examination of student outcomes in our own class. It began by trying to say, how could we predict student outcomes? And what we learned is something well known in the literature, that if you want to predict a student's grade in a college class, you should look at students' grades in college classes. The strongest predictor of grades in classes is grades. So we did that, and what we found is that if we look for 28,000 students who've taken our introductory physics course over the last 12 years, at their GPA in other classes on this x-axis, and their grade in the introductory physics class on the y-axis, what we found is that there's a strong correlation between those two things. The points that you see here with very small error bars are the means and the error on the mean for students in each bin of incoming GPA. All right. The dashed lines represent one sigma dispersion. There's lots of dispersion in this relation, very well determined in the mean. Two things we learned from this. First of all is that outcomes for students are very much perceived individually. One thing we like about comparing students' grades in other classes to their grades in this class is that that's what students do. Right? They think of themselves as a GPA. I'm a 3.8 student. I'm a 3.0 student. Right? So if you have a student who gets an A- and usually gets B's in classes, then you have a student, or a B+ and usually gets B's in classes, you have a student who did better than expected. Meanwhile, if you have a student who gets the same grade, but usually gets A's, it's kind of a disaster and they're not taking physics again. Right? So students perceive their outcomes very individually. But the other thing that was apparent from this is that there are overall impacts of courses on students. If you look, you will notice that all these points fall below a one-to-one line. If they got grades in physics like they get in their other classes, all those points would be here, but they're not. They're all below that. So we now calculate something we call the average grade anomaly for the class, which is the mean difference between their grades and their GPA. And for introductory physics, that's about a half a letter grade. This is the grade penalty of the class. You sign up, your GPA is going down. It's not your fault. Right? In fact, I could prove to you that these students on average are better than average students on campus. We give them lower grades because that's what we decided to do. All right. The other thing we learned is that we began to examine the performance of different groups. So this is that same introductory physics course. Now there are two sets of points, a set of light blue points representing the performance of male students in this class, dark blue points representing performance of female students in this class. At every incoming GPA, you have differences in performance. Those average differences are large, so that male students pay a grade penalty of about 0.3 letter grades in this class, and female students pay a grade penalty of about 0.6 letter grades. Same class. Two students come in with the same GPA, different outcomes. Okay. This started to look really like an equity problem for me. So I started talking to people on our campus about it, and my chemistry colleagues started telling their students not to take physics from us because clearly we were biased against women. Wait and see. So a first question that we might ask, which we should have asked much faster than we did, is this a problem with physics? Or is it some other kind of problem? Is it a more widespread problem? I'm ashamed to say that it took us 3 or 4 years to ask that question. I'm not sure why, because I guess I sort of felt like I wasn't allowed to, or something. But now we have done that, and it is not just a problem with physics. It's a much more widespread issue. This is Econ 101, an introductory econ lecture course. Very similar kinds of structures in a variety of ways, including that there is a substantial gendered performance difference in this class. Okay? We then went on to examine this across all the large introductory science and math classes on our campus and discovered an interesting pattern. So first of all, what we're seeing here is the average grade anomaly of the course on the x-axis. So courses that give out higher average mean grades are on this side, lower average mean grades are on this side. And then gender performance difference on the y-axis, so courses where female students outperform male students up here, where male students outperform female students up there. And I'll draw your attention to the fact that the gender equality line lies near the top of the graph. Okay? There's a pattern in the courses that you see here. There's a set of STEM lecture courses that lie here with very low mean grades, but also very large gender performance differences. And then there's a large group of STEM lab courses that lie up here with essentially no gender differences and slightly higher average grades. These are the same subjects. So what we're seeing here is not a question of physics, biology, chemistry. It's a question of lecture class or lab class. These two kinds of classes are different in a wide variety of ways, but one of the principal ones is they're evaluated by very different mechanisms. They have very different evaluative environments. This is the land of high-stakes examinations, mostly very mechanical examinations, in fact, often multiple choice examinations. A very inauthentic form of evaluation. Even introductory labs, even when they're not the best introductory labs, we ask students to do something more authentic than what we do in large lecture classes. Okay? So we discovered this pattern a couple of years ago, and we're immediately faced with the question, is this a Michigan problem or not, right? So we did try to find every other explanation that we could. We took all the information we have about these students and tried to find a way of explaining away, if you like, these performance gaps that we see. It's my class. I don't want it to be true. I would love to be able to say, oh, yeah, well, that's what happens, but it's not my fault. But I have not found a way to do that. All right? And so we've published all this kind of information. I think that these gender performance differences that we see represent what legal scholars might call disparate impact. So in the legal scholarship around discrimination, one way to prove discrimination is to find someone who says, I hate people like you, so I'm never going to do anything for you. Right? That's a hard way to prove discrimination, because people usually don't say that. The other way to prove discrimination is to show disparate impact on groups of people. And here we have an environment that we've created that has a disparate impact on different groups of people. And I think actually, we're kind of culpable. We should do something about it. Okay, so like I said, we wondered that next, is this a problem just with Michigan? And so we went to other institutions to see if we could get them to do the same analysis. This was in around 2015. At a time when most institutions were not ready to handle their own data, and very few institutions were willing to expose their data to analysis about issues like this. Maybe you can think about your own institutions and where they are about that right now. I think that many institutions have advanced a lot over the last few years, but it was very difficult to do in 2015. But we managed to do something. We did a small project with the Sloan Foundation called the Sloan Learning and Research Analytics Project that started in 2015. We got together 10 Big Ten campuses and regularized the data on each campus. And rather than sharing the data, we put the data in the same form and we shared the code. So we did the analysis the same way. Okay? This was quite painful compared to what it would have been to share the data, but that's what we could do. It was a trial, in a way, for larger collaboration. So we brought together about 50 people from 10 of those Big Ten institutions. And the first thing we did was to examine whether these patterns of grade, penalty, and gender performance difference are widespread or not. 10 institutions did the analysis. 5 allowed us to talk about it. Okay, well, that was all right. It was, 5 was enough. 5 was enough. So what did we find? Here's a couple examples, just to give you a sense. I'm going to show you plots that show those same kinds of figures for the same class, first semester engineering physics, on 4 different campuses. One of them is Michigan. I'm allowed to tell you that's Michigan. The others are 3 universities. I'm not allowed to tell you who they are. Okay? Gender performance differences, 0.23 letter grades, 0.24, 0.22, 0.15. Introductory econ, 0.3, 0.3, 0.3, 0.36. Introductory organic chemistry, 0.2, 0.25, 0.22, 0.14. Chemistry lab, 0.01, minus 0.01, minus 0.08, 0.09. Right? Really crazy similar. So why might they be so similar? Do we teach chemistry the same way on a lot of campuses? Do we teach physics the same way on a lot of campuses? It's actually a pretty similar environment. So it shouldn't have surprised us very much that we might find similar kinds of outcomes. Okay, this is a figure pulling all of those together. This was published by Becky Matz and a bunch of us in Era Open at the end of last year. You can go read the details there if you want. I just single out, this is the big Gen Chem lecture courses, often the first science class that people take. So the first science class that people take has very big gender differences on all these campuses, also gives very low grades on all these campuses, and both of those things give students messages about who belongs in science. Okay. So how could the same environment affect students differently? Male and female students in the same environment. Isn't giving them the same environment perfectly fair? When I made this slide, I thought, what a ridiculous question. How could the same environment not affect different students differently? Of course it does. But I think the model we had in our mind when we created this system is that fairness is equality. We give people exactly the same thing, and that would be perfectly fair. And I think this is evidence that it's not. Okay? So one way, of course, that this could affect students differently is that people might know that they are expected to perform differently. They might experience stereotype threat in an environment like this. So I'm sure all of you have heard about stereotype threat. The basic idea of it is that if you are in a performative environment and you know that people around you may expect you not to perform well, you're aware of that, and it consumes some amount of cognitive resources impeding your performance. It leads to performance that's a little bit worse. You don't fall apart, You don't fail completely. You do 5 or 10% worse. One more question wrong on the test. You know, just a little bit. I always like this example. This is the Solvay conference in the 1920s in Paris. A lot of famous physicists. Even the non-physicists recognize some of these people. That's how famous they all are. One of those people is Marie Curie, the only woman at that meeting. And it's impossible to imagine that every time she opened her mouth, she didn't know that the words she spoke would be taken in different ways from everyone else. So it's impossible to imagine that it doesn't have some effect on you to be in that kind of environment. All right. So I think it's a real phenomenon. It's really pretty well established in a bunch of different ways. Removing the threat reliably can reveal people's true ability, and that's kind of the goal that we might have. So when I think about these big classes, I think about the ways in which we try to give people the opportunity to really perform. And at the University of Michigan, one of the places where we do that is in athletics, you know. We do not make people swim in cold swimming pools. Trust me, they have the nicest swimming pool you've ever seen, right? Why is our introductory physics class not like that? Why don't we create a space where everyone can perform equally well? So I think that's the goal that we have in mind. We want to see our students at their best. So how might we address equity by design? How might we design for equity? How might we clear the track so that everyone can show us the performance they really can give us? I think there are a lot of ways to go at this. For now, what we're doing is exploring some changes to the ways that students experience the current evaluative environment. And I'll tell you a little bit about delivering social psychological interventions and reducing time pressure. The ultimate goal, though, really should be to recognize that this current evaluative environment is the problem. And if we could get away from it, we would be in a much better place. So my ultimate goal is to get to the point where we can stop relying on timed high-stakes examinations and move to some forms of evaluation that are valid and more authentic. There are lots of practical challenges to do that. Some of them have to do with the culture of the way we think about our teaching. Some of them have to do with practical issues of how we will evaluate all that work. They all need to be overcome. This is the 21st century. It's not the 20th century. Okay, so we have done some work with values affirmation interventions to see whether they might be effective at reducing these gendered performance differences that we see. So in the fall of 2017, we did 2 large random controlled trials at the University of Michigan. One was based in class, where 451 students in a second semester physics class sat down in the context of their lab and did the writing on paper. That's the traditional way to deliver these interventions. And then in an effort to scale these interventions and in a certain way deliver them around the instructors of the courses, we used this eCoach tool that you heard a little bit about earlier to deliver interventions to 1,850 students in 8 large STEM courses in an online intervention. So the first thing we saw is that the in-class intervention was pretty effective. What you're looking at here is female control students and affirmation students, and male control students and affirmation students, their performance in this class. So in this particular class, where they did the in-class writing, it had a pretty substantial effect. Seems to have narrowed, in fact, even closed the gender gap in that class. When we did the same kind of intervention online, we saw no significant effect. And this is a bit of a mystery. There are lots of reasons why it might be. In fact, when I tell this to any social psychologist, they immediately give me a list of reasons why it might be. They're not reasons that they gave me before we did the trial, right? But they're explanations of why they knew it wouldn't work. My general take on these is that this is great to see. And so, in fact, we have implemented in-class interventions in our big introductory physics courses this semester. We're hoping that we'll see it work again. But these interventions, to me, don't feel like they're a very robust solution to this problem. Yes, you have a question? Yeah, it was the very traditional values affirmation intervention that we actually heard discussed earlier. Students are just like the Harakevich intervention. In fact, this one is an almost direct replication of that. Right? Students are given a list of values. Students are given a list of values. They're supposed to select the values that are most important to them and then write about why they're most important to them. It's a 5-minute writing exercise that takes place just once in the beginning of the class. All right? Pretty minimal kind of impact kind of thing. And yet it can have real positive effects. Okay. A second kind of trial that we've been doing to see if we can alter the way people experience the evaluative environment is to reduce time pressure. So students always tell us that time pressure is a big issue for them in exams, and we wanted to see, is it really? Now, this is a place where it would be very difficult to do a random control trial, to tell your students half of you are going to get 50% more time and the other half aren't. So we didn't do that, right? I mean, this is a fascinating thing about using real classes as experimental environments. You have to think about issues in different ways. So we gave everybody 50% more time. We recorded the completion time for every student. So we had them swipe cards as they were leaving, so we know how much time every person took. And the idea was to test for shifts in gender performance difference against previous terms. And we also used a bunch of repeated questions to see what happens to the class. Do they do way better? Because if they do, then something's wrong with our design. We really shouldn't pressure them so much. All right. So we've looked at both of those issues. Now, let me go back. The button is quick. This is the gender performance difference for students who finish early, middle, and late in the group on exam 1, 2, 3, and 4. And overall, the gender performance differences remain significant for all of these groups. So adding more time may or may not have affected their sense of pressure. It certainly didn't affect the gender performance differences that we see. Okay. We also had these 41 repeated questions, and we did an analysis of how they did compared to prior terms for all 41 questions. A couple of fascinating things emerged from this. We can see the effects of instruction. When you teach a topic better in a particular term, students move a lot, right? The noise in these is much larger than the noise in the actual measurement, right? So they're different. Students take the class at a different moment, and they do a little better and a little worse on questions. That's kind of nice to see that it would matter a little bit what you do in class. The overall student performance improved about 4%, averaged over all of these questions. If we throw out the 2 sigma outliers, it's a little bit less, but it's still significant. So if we give students 50% more time, they do a few percent better. Now you're faced with the question, well, do you want to give them 50% more time or not? There are 700 students in the class, so 50% more time is basically 700 hours of human effort more. It's not trivial, right? It's 10 weeks of full-time work that goes into that extra hour. So interesting questions to think about. Okay. So we've been thinking a lot about how can we achieve a really sustained reform in these classes. It comes from doing this kind of work of examining them, thinking about how could we get these courses really to the next level. And I believe that this kind of reform requires new kinds of teams. We can't expect instructors who, as we have heard in this conversation, often don't have very much training at all, to step into this very different kind of teaching environment and create a course that creates great learning. So I think we have to build collaborative structures around course design and delivery that I think should mirror the way we do our research on big science projects. We should put together a team of people that have all the expertises that are needed in order to do this. And it should be a team that includes faculty members and postdocs and graduate students and undergraduates and pedagogical experts as well. And I also think there are lots of ways in which we need to use information technology to support these classes. This is a place where technology can be very useful, much more useful than it is in a course of 30. We've been working on putting together prototypes for both of these kinds of things at Michigan. The first one is something called the Foundational Course Initiative. It brings together STEM education practitioners with researchers, but also instructional designers, experts in assessment and analytics, and in student support. Puts those people together in a team that will work together for 3 years on a class. Not just for a summer, but will actually go to work on a course for 3 years. We convinced the provost at Michigan to put $5 million into this project, which is being run from our Center for Research on Learning and Teaching. So that's building the team around this. We've also done a bunch of work to build information technology in this digital innovation greenhouse that we put together. Again, bringing together practitioners and researchers, but now with software developers and user experience designers and behavioral scientists who can build tools that might enable us to support this kind of work. It's now part of the Office of Academic Innovation at the University of Michigan. And I'll just very briefly mention 3 tools that we've developed. One supports writing to learn activities in giant classes. We heard some about writing to learn activities earlier today. A very powerful way of learning more about what students know and also creating more learning in them. A tool called Problem Roulette that allows students to practice thousands of prior exam questions on our campus. And then this eCoach tool, which lets us do computer-tailored communication, coaching each individual student on what's happening in their course in a way which is aware of who they are and where they are and what they're interested in. It allows us to tailor what we say to students, how we say what we say, when we say what we say, and even who speaks. Just to give an example, we use testimonials from peers a lot in this system. If you want to say you need to start studying 2 weeks before the exam and you say it as the professor, forget it. They don't believe you. But if their roommate says you need to start studying 2 weeks before the exam, they might do something about it. So testimonials from peers. Okay. Local reform efforts are great. I want to finish by talking about what we need to get to the next level. I think most of you have local reform efforts going on, right? We're all trying to do this. We're doing it here, we're doing it here, we're doing it there. We need to bring those together. This is a great way to bring them together, to have a conversation like this, but I think we need to do more than that. We need to build a collaborative national movement that will establish new norms for these classes, right? We need to change what people think is a normal, big introductory science course. And I think the way to do this is to learn from our experience addressing other giant scientific challenges. When we wanted to map the universe, we put together a team of people with a couple hundred scientists from all over the world. If we want to change introductory science courses, I think we need to put together a team that isn't just isolated on each campus, but really comes together. All right? So we may also need a new form of motivation. We heard a lot in these conversations about the way in which evidence is not enough. 10% improvements in learning aren't changing anybody's mind. So I think we should focus on equity. I think that is a thing that can excite a level of passion and engagement from people that is not present when we tell them that learning will go up 10%. Right? So a course cannot be excellent unless it shows that it's equitable and inclusive. Okay? So I'm now working to put together a collaboration called Seismic, the Sloan Equity and Inclusion in STEM Introductory Courses project. I know the word seismic may not resonate as nicely in California as it does out in the Midwest, in the middle of the North American craton, but that's what it is. We're going to draw together reform efforts from about 10 big institutions, and our goal is really to focus on equity and inclusion as the thing that we will study and work on together. And I'll just finish by saying the goal is really to have an array of multi-institutional examinations of equity and inclusion of the kind that we hinted at in that 5-institution project, but to really get a picture of the landscape across all of these places, to have multiple independently funded research projects that allow us to do experiments on multiple campuses at the same time, and to use that kind of mechanism to enhance the research and development efforts that all of these campuses have. And at the end, we hope we will have like a new standard for how people will decide that their courses are good. Is it really an equitable course or not? That's the standard I hope we will have. And I'll stop there and be happy to take any questions people have.
Okay. We have time for maybe 2 quick questions.
Did you look for any correlation between the gender of the instructor?
Yes, many people do. And we see no obvious signals. It's not like you can throw a female instructor in the room and make these effects go away. And that's not, I think, too surprising, but it is true. Yes?
How is the percentage of men versus women in those courses? And also have you tried to separate them so you just teach the girls only for men and the male instructor versus only for women?
We have not done the second. And how is it presented to them? I mean, what do you mean?
What's the percentage? I mean, how in current courses, how many male?
Yeah, it varies enormously across those introductory science courses as it does everywhere. So in my introductory physics course, it's about 28% female because it's largely engineering students, and that's their representation in that college. In the introductory biology course, it's 56% female. So it varies a lot. It doesn't look like there's one parameter describing all of this. That's why I turn to the assessment as a key. You know, that's the one thing these courses all do share. Yeah, one more. Okay. Okay. Yes, so I could give a whole talk about the intersections of identity, but not in a half an hour.
Thank you.
Okay, I'll give you this.